Thanks everyone for having me here today. It's actually my first talk, so I really hope it goes well. But I really just want to be useful to y'all. So honestly, feel free to interrupt me if you have any questions. But we're also going to be hanging out with my team down here after the talk, so we can have more conversation and answer more questions. But yeah, today I'm going to be speaking about improving CI performance. We made a lot of progress this year in this area. I work at Block and I'm on the Android developer experience team. At Block, we ship products such as Square, Cash App, Tidal, some others if you didn't know. So why do we focus on CI performance? We really want to listen to our developers, and at the beginning of this year, we read from our surveys from our developers that CI builds are slow. And so we wanted to get more specific than that. And we thought about what part of CI do they interact with, what gets in their way. And of course, as we're all probably familiar with, it's the PR builds and the CI that runs on that is most likely to get in the way of developers from being more productive. And so we focused our efforts on specifically PR build duration. And we wanted to measure not just all the worker hours that goes into it, like computer time, but wall time. So our goal is to simply reduce the PR wall time. I was really glad to actually see in one of the research yesterday that came up that every minute or unit of time that you're shaving off of that, the builds, it helps in a meaningful way. Like it's linear. And so we didn't set a goal when we first started. We just wanted to pursue the biggest opportunities. And to be clear, the non-goals of this is to optimize CI cost, to shave down just worker time in any part of the system. That's not our focus, because we wanted to focus on what actually matters to our developers. And we're also not going to focus on the post-merge CI builds. So after you land your code, the tests that happen after. These are, of course, very important things. We will continue to look at these things, but our focus is not that. It's to save our developers time. So this is what we were able to achieve this year. Our average PR wall time dropped from around 60 minutes to 32 minutes in the last 2 months. And if you add that all up and multiply by the number of PRs there are, if you project it out for a year, it's about over 10,000 hours saved per year. And recently, we're hearing feedback from our developers, such as Ray. I love this comment. I can't get over how smooth CI has become recently. PRs are auto-merging quickly. Green Master is crazy fresh. Wow. So we don't get to hear this type of feedback very often, so it was very welcomed. So I encourage everyone to just provide or give thanks to all the teams around you that's doing good work. Okay, so I'm going to step back and just give a little more context into who our customers are and the situation around it. So we have 200 developers, and this is specifically for the point of sale portion of our product. So not Cash App. This is specifically for point of sale Android builds. It's in a mega repo, and we have over 6,000 Gradle modules, 5 million lines of code. And what we ship from this repo is 7 apps shipping to Google Play Store. In terms of hardware, we have Android mobile, tablet, and our custom point of sale hardware, such as register and terminal. Okay, so let's get into the details of our PR build. The average PR build has 750 shards or types of jobs, and it could be up to 1,500 for a full build. We do try to skip as many of these as possible, depending on the contents of the PR. And the types of jobs we run are checks, lints, compiling tests and apps, and all sorts of tests, such as unit tests, UI tests. And in total, it adds up to about 60 worker hours. So these are instance hours charged by AWS in our case. And this doesn't include the UI test execution, which runs on its own emulator farm. So it's more than 60 hours of work. Again, just want to mention, we started out with 60 minutes of wall time duration on our PR builds. and we have about 100 PRs per day. So a little bit about our CI system. It's called Kochiku. It was built over a decade ago in-house, and we still love it. We thought about migrating a few times, but I think we're holding on to it. And the CI workers run on AWS EC2 instances, and there are ephemeral containers, Docker containers that run the job. And so in terms of how many containers are running on an instance at a time, it's 1-to-1. But between every job, new containers are started. For more context on our CI and strategies around scaling it, I highly encourage you to check out this talk. It's on YouTube. It's from last year's DPE Summit from my teammates Inez and Paul. Inez is right here, so go bug him after if you want to learn more. We cover topics such as shard avoidance, so the job skipping, avoiding as many UI tests as possible, and scaling Git for our needs. Okay, so let's get into actually trying to improve CI performance. So one of the most valuable things for me was to be able to actually take the data and understand it. And, as a human, like, at least for me, I'm very visual. So it really helped to visualize a CI build. This is not an aggregate of all the builds. You just take sample and you're able to visualize it. And the most powerful view that I've seen is a waterfall view. So this is just a screen cap of what we built. It's pretty basic, but gets the job done. And I know this video is scrolling fast, so I apologize for that. But you're able to see all the jobs have its own row, and you can see the width. The width represents duration, and the small gray bars you see is queuing times. We add some other details on there. We also, let me play that again. I don't think I can. But we also add things like dependencies between different jobs on there. It's a very helpful, interactive way to understand your build. So once you have a tool like that, you can just find some bad builds, some really long-running builds, and just get a sense of what's actually happening. I'm going to show some samples that led to investigations and solutions in a little bit. But again, just wanted to highlight that this has been super helpful to me, and I would encourage anyone looking at the CI performance effort to have something like this. I just wanted to get a sense of how many people have access to a tool like this. I don't know what other CI providers provide. So who has access to a build waterfall view? Okay, it looks like about half. Who doesn't know if you have access or not? Okay, cool. So it sounds like there's maybe some opportunity. Good to know. Okay, so let's get into the actual improvements we made. So here's a preview of what I'll be talking about. There's 4 projects. First one is reducing queue times. Second one is eliminating spot interruptions. Third one's bundling the Gradle cache. And last one is improving disk I/O. All right, let's get into reducing queue times. So here's a screenshot of one of those bad builds in the waterfall view of it. So you can see that the gray bars represent queue time and green bars represent the actual runtime. And if you look at the bottom, you see how much longer we're queuing compared to actually running. So there's a huge inefficiency here. And we measure queue times before this, we chart it out, but it really helps to load it up and actually see, if I eliminated these gray bars, it would make a huge difference, right? So it helps build up the sense of urgency around it. But you do look at the charts, and I look at it in the aggregate. And in this case, we measure P90 queue time for jobs because we don't want any jobs to be queuing super long. And I know the numbers here are small, but that's 30 minutes at the top. So sometimes, this was in November, in some weeks we would queue up to 30 minutes for jobs. We never want that. But, I want to also see, is queue times a solved problem for y'all? How many, are still dealing with queue times in CI? Okay, good. I mean, not good. but I'm glad I could maybe add perspective. Okay, so how much will it cost to actually improve this, right? I think we all immediately think, okay, we're just going to have to provision more workers. So in our case, our situation was we have the self-managed EC2 instances. We have full control over the AWS account. And AWS charges per vCPU hour, right? So if you think about it, in theory, we have a certain amount of jobs to run, and they run on these instances. Shouldn't we only be paying for the runtime of those jobs? And so it doesn't matter if the job started now or in 10 minutes. Like I should only be paying for what I'm running. And so the theory is that total job duration should be one-to-one with the compute hours that we're charged from our cloud provider. So maybe it's actually free to scale up and reduce queue times. And so we wanted to actually try it out and see. Some of the things that we want to be careful about is the reliability of our downstream services. So Artifactory is our dependency store. We have a remote build cache infra. We have a CI secret store. So you will increase the traffic to those things as you increase the parallelization, of course. So monitor the reliability of those as you experiment with this. There's also some small details such as service quotas for AWS and available IP addresses for your instances. And the thing we're most curious about, of course, is cost efficiency. So is it actually true that we shouldn't be paying more when we run things in parallel? And so you can see in the middle of that chart that we did lose some efficiency in this ratio. And that was actually due to a bug that we had in our code where we weren't freeing up those resources when jobs got aborted. So it exacerbated that issue and we were able to fix it at that time. And so after we fixed that bug, we actually saw efficiency go up. So it turned out to be true that we can just simply increase the capacity in our worker fleet, and we're not going to pay anymore. And so looking back at P90 queue times after this change, you can see this is charted on a daily basis. You can see that we brought down the queue times by scaling up our fleet by 35%, and the queue times are stabilizing and consistent around 1 minute. And in terms of the PR build wall time, our North Star metric, it reduced it by 5 minutes. Okay, so that was queue times. Let's get into the next project, which is eliminating spot interruptions. All right, so let's check out another build waterfall. You could see that here there are some jobs with different colors. And the one at the top, we see 2 orange bars and a green one. What's going on here? So the orange bars represent aborted builds. So for one reason or another, they didn't finish and the job had to be tried again. And so we see that many different times on the screen. And we want to understand how often does this happen? So instead of looking at just how many jobs get aborted, we also want to understand, more importantly, how many builds that have many jobs within it have aborts. So I know the text is small, but on the right hand, you can see the percentage of builds that contain an aborted job. And it ranges from 40% to 70%. So 40 to 70% of builds is suffering from this issue and maybe slowing down because the jobs have to be retried multiple times. All right, so let's dig into what causes these aborts in our case. It turned out to be spot interruptions. In case you're not familiar with spot instances, here's a definition. You can launch spot instances on spare EC2 capacity for steep discounts in exchange for returning them when Amazon EC2 needs the capacity back. When Amazon EC2 reclaims a spot instance, we call this event a spot instance interruption. Okay, so we're using spot instances to save on costs, right? How are we going to get around this? Are we going to just pay up? It seems like that's the answer. So we need on-demand instances if we want to solve this problem and improve performance. So I guess it's time to pay up. But of course, we do this. We buy developers new laptops every few years. And so it's definitely worth considering. So we talked to our cloud economics team and understand what the cost modeling is. And they actually mentioned AWS Savings Plan. And so this is a cost-saving strategy that AWS provides. There's also things like reserved instances, but they tell us more about how this works. And we're actually able to provision on-demand instances at a highly discounted rate. And so we had to do some hand selection of exactly what instances would fit with our workload and fall into the savings plan. But we were able to find some instances to start an experiment with. And so we moved some of our workers to be on demand, and it was going well, so we continued to do it. And it actually turns out that with the savings plan, we moved completely from spot instances to on demand and keep the same efficiency in terms of cost per hour. So that was a huge win. We thought we were going to pay a lot more, but now we're running on demand instances. And in terms of interruptions, they should go to 0. Again, I mentioned aborted jobs can happen for other reasons as well. So aborted jobs don't go completely to 0, but spot interruptions did. And in terms of wall time, that shaved off 7.7 minutes off the average PR wall time. So we're just going to fill in this graph one at a time. All right. So I highly encourage you to pay attention to your retries that happen within a build because they may be affecting your performance. Okay. So let's get into something called bundled Gradle cache. As you could tell from the title, it's around the Gradle cache. A prerequisite, I think, for considering this is that you're already using the remote build cache and you have a pretty high hit rate. If you don't have a high hit rate, there may be some things going on that you can improve on. And secondly, this is most helpful to ephemeral CI containers like we have, because it's an optimization that we make on both of these scenarios. Okay, so what's the opportunity? How did we find this? So each Gradle build we have the build cache, and each one of those fetches from remote cache is a separate network request. And we have around 30,000 requests per Gradle invocation. There's also dependencies that need to be fetched for the build. And this happens every time for every job because we're using ephemeral CI containers and we're not saving any persistent cache or state that the job can use. So given that these are all fetched separately, they have their own network cost. And if you have tens of thousands of this, you could see how it could really accumulate on performance. So the idea is to pre-populate the local cache before you run the build and stop fetching so many tasks individually. This would eliminate that network overhead and maybe affect performance. So the idea is to get closer to somewhat of an incremental build on your PR CI builds. So how do we implement it? We wanted to make sure we had as high of a hit rate on this local cache as possible. And so again, with the theme of incremental builds, we push this cache from main CI builds. So we run a task, we run a Gradle invocation in main, and if it succeeds, then we'll bundle the Gradle cache directory and we'll upload it to S3. And the path that we use is the commit SHA plus the name of the shard, which is a unique identifier of what task you're doing within the job. And so now we have a way to identify exactly what run and what type of job is this cache contains. Okay, so the cost of this is strictly worst performance on main CI builds. And that's kind of why I mentioned in the beginning that our non-goal is to improve main builds because developers don't notice this as much. So it's a cost we're willing to take. And of course, there's some extra storage costs associated with storing these bundles in S3. So the next step is on PR builds, pull this cache and try to find the most appropriate bundle to apply. And so we start with the base commit of the branch. So this is where you merged or where you branched off from main. and we check 10 commits from that going back. And so we check 10 different commits, or up to 10 different commits. We check S3 to see if there's a hit. And if there is, then we download it and we extract it to the local Gradle cache. So the outcome of doing that, it was successful. We have high local cache hit rates. It reduced traffic to Artifactory. And the number of remote cache requests reduced by a factor of 10. We used to have roughly 30,000 cache requests to remote cache, and that fell to around 3,000. And the duration of the compilation shards improved by 17 to 28% across the different jobs. And in terms of the average PR wall time, that reduced by 3.8 minutes. All right, last one, resolving disk IOPS bottleneck. So guys at Peloton also mentioned this. I'm really glad that some other people are aware as well. Crazy thing about this is you can be doing everything right with your Gradle builds. You can follow all the advice that is on the Gradle website and everything you heard at these talks, and still be leaving 50% of your performance of these Gradle tasks on the table. So this is exactly what happened to us. Like, we have Gradle experts within our company, and somehow we missed this. So let me show you like what we saw and how we stumbled upon this. So this is a build scan in DevVelocity, and you can see we have many tasks that got avoided because it hit the cache, and this is after bundle cache. So these are from local cache as well. And you can see that on the right-hand side, these tasks that are cached are still taking an hour and a half of serial execution time. Like, why is this task? Like, isn't that supposed to be close to zero? Well, there's the fingerprinting step that happens in order to compute the cache key to be able to fetch these tasks from cache. And it turned out that was the thing that was slowing these tasks down. And we look a little deeper, and it looks like it was due to limited disk IOPS. So IOPS is I/O per second, basically how many operations of read or writes can you do on your disk. And so this especially affected local build cache. Actually, I think it's just the part where it computes the cache key uses some files on disk. So in order to talk about the solution, got to touch on how EC2 does disk storage. And so this is just a screenshot of the M6 instances. And you can see that many of the instance types only allow EBS. And some of them have attached SSDs. And so EBS is Elastic Block Store. It's a network attached storage, and it's the default option for most instance types. And you get 3,000 IOPS free. And if you want more than that, you have to provision more and pay more. Another option is this attached store, where these disks are physically attached to the instance, and they're in contrast to the 30 IOPS that you get from EBS for free, you get millions IOPS, like literally millions, and no additional cost if you're already provisioning these instances. But they must be mounted. If you just leave it, if you just start up this instance, it's going to be useless to you unless you mount it. So our situation was we were running on these instance types, although they were very beefy, like we were running on M7, like 4x large instances. So super beefy in terms of CPU and memory, but severely bottlenecked because of this 3,000 IOPS. And the crazy thing was, I mentioned earlier that we selected instance types that would fit the savings plan. We were actually provisioning instances with the disk. So we could have just been mounting it. But they were not yet mounted. We didn't know it was a problem. So what happens when you do mount it? Our simple solution was to basically just mount the whole Docker container. And what happens if you compare that screenshot from before, the serial execution time for these tasks from cache go from an hour and a half to 17 minutes. So after we resolved it, we shipped it, the duration of our compile jobs were cut in half, And this had a 12-minute reduction on our average PR build time. So that was the last one. This was our journey this year to date. Went from 60 minutes to 32. I added pointers to all the projects. They had various levels of impact, but we had, just to recap, we moved from spot instances to on-demand to be able to eliminate the interruptions and eliminate the retries around it. We implemented the bundled Gradle cache strategy to be able to save on the network overhead and the back and forth. We reduced queue times, and we gained the extremely valuable insight, which is we could continue to scale up. And of course, we'll linearly pay for, or proportionally pay for scaling up, but we're not going to pay extra just to run the same amount of jobs at the same time. And lastly, there was resolving the disk IOPS bottleneck with attached SSDs. Some other takeaways I just want to highlight is that focus on wall time for developer productivity. We did get some efficiency wins from these projects, but I'm really glad that we didn't get distracted by all the different ways that you can optimize some job in CI, because chances are just optimizing a random job is not going to affect the wall time and the productivity of developers. And secondly, want to highlight that visualization waterfall tool. It led to at least 2 of the projects that we mentioned here. And lastly, it was super valuable to be able to collaborate with our CI teams and our cloud economics teams. I hear sometimes like, or maybe it's just a way of thinking that we have where we know our expertise, we know our domain, and we just try to do as much within it. But I'm kind of new to this space, and we were able to spot these opportunities because we're able to think outside the box and look for some other opportunities outside of our domain. And, these teams are working on general solutions. I don't think they're looking at build scans to see how long fingerprinting is taking. So we need to team up with other teams at our company to be able to collaborate and find these types of solutions. So that's it. Thank you so much for coming to my talk. I hope it was helpful. So I'm going to skip the Q&A because we have a few members here. We'll be hanging out just right in front of the stage. So feel free to come up, say hi, ask questions. We welcome it. I'm going to skip the Q&A. Thank you.